Hello, everyone. Welcome to the TriboNet seminar on evaluating the Stribeck curve in the boundary lubrication regime using a force-controlled tribometer. Today, we have with us Professor Satish Vasukailas. He is a professor from Indian Institute of Science, Bangalore. He obtained his BTech from Government Engineering College, Thrissur, and his PhD from IISc. And then he had his postdoctoral research at IISc till 96, and then he did as a guest researcher in the National Institute of Standards and Technology, USA. Then he is carrying out his research in tribology, friction stir welding, processing, metal forming, and other interests. And further, he has published a lot of papers, which includes 150 peer-reviewed journals, and he was also authored on a course in material science in NPTEL program. We are really very happy today in TriboNet to have a distinguished professor like Satish here. Thank you for accepting our invitation, Professor, and over to you.
Yeah. So let me go to the pointer options. Are you able to see my laser pointer?
Yes.
Okay, great. So thanks to Manoj and Xavier and others for inviting me to give this talk. This is something that is new to what you call me, in the sense that given online talks many, but through organization like TriboNet or TriboGeek, your organization called TriboGeeks, right?
TriboNet, sorry.
TriboNet. So there's some Tribo. Anyway, it is a great honor for me to give this talk. So today I'll be talking about evaluating the Stribeck curve. I should also mention that Stribeck curve is something that many of you will have heard about. So sorry if I am patronizing many of you, but we are also struggling to evaluate this Stribeck curve in the exact nature, but we have come close to that. Okay, so I have to thank people first who have collaborated in this work. My students, Pranay, who started this post-tribology work. This is something that we feel is necessary and different from what is being done today. And Adarsh, who is just submitted his PhD, and so he was a fellow supported by IOCL and the Federation of Indian Chambers of Commerce and Industry. Vikas Kumar Singh is also supported by the central government, in the sense that he's got what is called the Prime Minister Research Fellowship. And Prasad is a student from ICT Mumbai. So he had come here, and he's leaving today after a 7-month stay in our lab, where he evaluated several esters, esterolites, and several what you call organic molecules as friction modifiers. And this work, though started independently, was later on supported by IOCL. I should thank their former chairman, Ram Kumar, and several other collaborators there, Dr. Sarita Seth, Ajay Kumar, and others who were there, who helped us with the project. So what is Stribeck curve? All of you know the Stribeck curve. For those of you who don't know, this basically relates the coefficient of friction versus the viscosity of the oil into the velocity divided by the load. So let us say I keep the viscosity and the load constant, and if I reduce the velocity, what happens is, or when I reduce the velocity, what happens is the gap between the two surfaces is reduced, because when I increase velocity, the pressures in the lubricant will increase and separate the surfaces. And this region is called the hydrodynamic region, and this has been pretty well studied and understood. So when you have separate surfaces separated, then you wouldn't get much of, you would not get anywhere actually. And you would also, what you call, the friction will be pretty low and only be dictated by the viscosity of the oil and viscosity index of the oil, because temperatures can increase during operation. But as I reduce the velocity, what happens is the surface comes closer, and then you will start getting partial contact. When you start getting partial contact, the friction starts to go up, because now you have a solid contact. And when the velocities become still lower, there's a large contact between the two surfaces. And this is what is called the boundary lubrication regime. While these regions have been quite well understood, it is these regions that studying becomes very important. And remember, in any tribo system, you will always have what do you call different tribo system. You always will have a start-stop cycle. But if you take, for example, an IC engine, you will always have a boundary lubrication at the top dead and the bottom dead center. And especially at the top dead center during the compression cycle and the power stroke, starting of the power stroke, because your pressures will be significantly higher than the exhaust stroke that happens. And though many of us believe that there are several articles written that IC engines is end of its road and all are going to electric. But I do believe that IC engines still will play a major role for years to come with different kinds of fuels. For example, hydrogen or the biogases and ethanol and other things. So this IC engines and of course in all other machinery, when you have a start-stop cycle, you will get a boundary lubrication where your friction goes up, and this leads to wear of the surfaces. So therefore, understanding the nature of the Stribeck curve of a lubricant becomes important. So let us say that you have a Stribeck curve and you have a friction, but you need to reduce this friction as much as possible. So how do you reduce this friction? One way is to have additives in between in the oil so that it forms a tribofilm on the surface, which doesn't really allow direct metal to metal contact and can reduce frictions significantly. But you still need to evaluate this. This portion evaluation becomes difficult because doing experiments at low velocities is not easy. And as I go further, you'll realize several things play an important role other than just the oil and the additives. So in this is basically an energy loss system, what do you call curve. So it has to be better depicted. Now, what I would like to introduce at this point of time is what we call the force versus displacement control tribology. This is a concept that has not been studied in depth, possibly because as we try to search for literature, not much of it is available on this. And we would like to differentiate the two systems of interaction. So in a force control system, the asperity interaction control the motion of the system. In other words, the kind of interaction that takes place between two surfaces will be dictated by the forces that happen or that are produced during the asperity interaction. Okay, this is different from the displacement control tribology or displacement control system, where you are moving the surfaces at a known displacement rate. So if I am applying a force to the system rather than a known displacement to the system, what would happen is that when I'm having these asperity contacts, the forces would go up. And when the slip takes place between the asperities, it can go and strike the next asperity at a much higher velocity than what we envisage in this thing, and like a stick slip condition. And of course, if we have a random surface, the stick slip phenomena may be less pronounced, but in any tribological system, even if you start with a random surface and if you have boundary contact, your surfaces start to develop a certain lay on the surface or certain morphology of the surfaces, which make it more of what you call non-random surface. So, and this basically depends on the overall stiffness and inertia of the system. Larger the stiffness, more would the system become a displacement controlled. So larger the inertia of the system with higher stiffness, more would the system become displacement controlled. I will explain this in this graph. So if I basically any tribo system you take, there are two things that are there in the system. One is the inertia and the other is the stiffness. So if I have a system with low inertia and low stiffness, I will become a strongly force controlled system. So let us take, let's say, a simple pin-on-disc machine where you have an arm that is holding the pin. Now, if the arm becomes lesser and lesser stiff, And when I start getting these asperity contacts, the vibrations will be much larger, and basically the forces that are developed between the two surfaces will control the tribo contact. And the other, when my stiffness is large and if the inertia of the system is large, then it becomes more of a displacement control system. But remember, even if my system is large towards very low velocities, even if I have inertia, it can go into a force controlled mode. So there are several studies done on this thing, not too large, but there are some important work done. One of these systems that, I mean, basically I'm depicting here what is the force control system. I have a mass with a tribo contact here, and I'm applying a known force through a spring. Of course, there'll be a damping of the spring also. But if I pull this spring and I release it, then this thing will oscillate and die down. And the dying down depends on the damping of the spring, and but also or even the air effects and other things. But the tribo contact also will play a significant role in the damping when there is a contact. So let's say I add a lubricant in between over here. The lubricant will definitely reduce the damping. So depending on the damping, damping reduction, I can kind of predict the behavior of the lubricant. And remember, when it is oscillating in the ends of the oscillation, what happens is that the velocities become zero. So definitely you move into the boundary lubrication regime. But the problem with this kind of a system is that if I want to control the amplitude of the oscillation, then what happens is I have to pull more, which means I have to increase the force that is being applied also. Number one. Number two is that if I want to increase the normal force, I have to increase the mass of the system. When I increase the mass on the top of the system, then the total frictional force also go up. So can I do something that differentiates these two things, or can be independently controlled? So there has been one more tribo system developed by Ivan Krupakov from the Czech Republic, where they studied the ball on what do you call that, socket joint. Basically, this is a what do you call ultra molecular weight polyethylene cup, and this is the sphere made of whatever material you want. And basically, what they studied was the effect of the roughness on these or different kinds of textures on the surface. So they put it on a machine like this, where you take this to a certain angle and release it. It will start damping, and the damping will be dependent mostly on the tribo contact. There's nothing else coming in apart from the air drag that is there. So air drag has to be accounted for in these things, which is not an easy thing, because air drag is going to be proportional to the velocity of square of the velocity of sliding. And if I want to increase the normal load over here, automatically the frictional load also goes up. So I can't independently do this. And if I want to increase the energy of the system, either I change the oscillation angle to a very large angle, or I increase the mass. But the moment I increase the mass, the frictional force also goes up. But they have got some very interesting results. And one of the important things in this finding was that the results they get on the friction that exists here and in a displacement controlled tribometer that is generally used for studying this hip on ball and socket joints, I mean hip joints, are quite different. And they were able to differentiate between different kinds of surfaces. So if I have a non-dimple surface, it will be like this. And if I have a certain kind of a dimple, I will get much slower decay of the oscillation, which means that it is having lesser friction. And another interesting tribometer developed was by Jean-Michel Martin and his team from Lyon, where they had this tribometer where you pull this spring and you apply a normal load with the tribo contactor. You pull the spring and you release it, and then you study the oscillation dying down by using a laser measurement device. So here they were able to pick up the differences between two oils, or two organic molecules. One is the pure glycerol and butylene glycol. You could see that when you had butylene glycol, it goes up to 0.5 seconds, whereas it is less than 0.4 seconds, clearly saying this is a much better lubricant. But the thing is that this lasts for a very short period, and then many times using this to discern the thing becomes difficult. And furthermore, if I want to increase the normal load, I'll automatically increase the frictional load, and the oscillations will die down much faster. Another interesting machine developed by Norimune Soda can do the same thing, but this is similar to what Ivan Krupakar did in a different tribo contact. But a beautiful machine developed in the 70s, if I'm not mistaken, from the University of Nagoya in Japan. And then if I go for a displacement control system, I should be able to measure the force. But if I have to measure the force, I have to put a sensor. And the moment I put a sensor, the stiffness of the system changes. And this creates a problem, especially at very low sliding velocities, because then it will lead to stick slip, and the sensor stiffness would play a very critical role here. So this creates a problem in studying friction at very low velocities, or when the friction is higher. So we wanted to build a machine that will evaluate all these things. But important aspect is that none of the sensors used to measure the data changes the stiffness of the machine. This will enable interaction taking place at the sliding interface. Assuming that the rest of the machine is stiff, we have made very stiff machines with deflections of few tens of nanometers for every Newton force that is there, and should be able to evaluate the actual components of the interaction taking place. We need to have very high resolution and accuracy of data acquisition and high speed of data acquisition. And so we should be able to differentiate between force and displacement control, especially we are interested in the force part of it. And change in stick slip velocities as a function of stiffness also can be studied by these machines. So we had made an initial machine, which I am not explaining here, but basically what we did was we had this machine. So this is for a C6 molecule, that is with 6 carbon molecule, and you could see that it takes around 140 seconds to die down, and then you have a long tail. This long tail we assumed was because of the transition from sliding to fretting. And remember, sliding to fretting clearly indicates there is some thing in the system that can affect the stiffness. But in this machine, we did experiments with different kinds of fatty acids from C6 to C18. And we could clear, this is the damping of the system without a tribo contact. Remember, in the other machines, damping of the machine in different type of contacts is going to be difficult, because getting no load data is many times difficult is difficult in those machines. Damping in no load conditions. But this, we can get damping in no load conditions and damping with the contact. I will explain the machine, the new one that we have developed, which you understand what is happening there. But using this machine, we were able to clearly differentiate. When we calculate the coefficient of friction, we were clearly able to differentiate the thing. So basically, coefficient of friction was calculated by the rate at which this damping takes place. So if this damping rate from one cycle to the next cycle, if there is X amount of energy that is being expended, and this X amount of energy expended is basically because of the whole sliding distance. So the energy expended by the sliding distance will give you the coefficient of friction. And so we are able to clearly differentiate between different molecules. So, but this machine had some stiffness issues, so we developed a new machine. But I'll show you how we could represent these results in different ways. One of the ways was a spiral plot, where you start the oscillation at let's say the velocity or angular position of 0, and then the velocity goes when it comes to the maximum position, it becomes 0, and then as the oscillations are going on, the oscillations die down, and this is what is picked up in this thing. So basically, if I can get if I know the gaps between these subsequent cycles, then the gap is large, it means your friction dissipation is large. If the gap is small, it means your friction dissipation is small. So what we did was, based on the gap that is there, we made color plots. So basically what it means is that if my gap is large, I'll put red color, and my gap is low, I will put green color. You can see here C6 molecule is almost red, but if I go to C18, which is stearic acid, sorry, you can see there is a large green area, which means the stearic acid is a much, much better boundary lubricant than C6. But the interesting thing is if I take C14, there is no very less red region, which means at higher velocities, which is basically a bigger radius over here, the higher velocities, the damping is much lower, which means C14 is possibly a better molecule at higher velocities. And we also made what is called a rectangular plot. Basically, a rectangular plot is when you take the damping curve that is coming down, we basically, what we do is we normalize the amplitude to 1, and depending on the rate at which the amplitude drops, we color the regions with different friction. So here also, suppose it's green, it means that the change or the difference in the amplitude from one cycle to other cycle is low. And if it is red, it means the difference in amplitude from one cycle to the next cycle is large. And so you can see here also it picks up C18 very well. And remember, I showed you a tail. So this tail also indicates at what angle the fretting is starting, which will tell you that which is a better lubricant in the fretting region. So if I have this amplitude as the maximum one we have plotted as 0.75, if I have this amplitude low and the color regions being indicating again the energy dissipated in that region, which is in the fretting region is going to be much lower, I can say this in fretting, this is a much better additive or much better organic molecule there. So we could publish a few papers from this work, but we were not happy with several aspects of the machine, especially because doing experiments at higher temperatures were difficult, and the tribo contact here was a moving tribo contact. So I will come to the machine that we developed in the second generation. We have come to a newer machine later on where we use, instead of using a bearing over here. So basically what we do here is we have a pendulum that is hanging between two bearings, and this pendulum has a disc attached to it, and this disc can be immersed in a lubricant, and you have a tribo contact which is immersed in this. So when I take this pendulum to a certain angle and I leave it, it will go from position 1 to position 2 to position 3, then come back to position 4 and come back to position 5. So this difference in the angle gives you the energy dissipated in one cycle. So basically that's what was done before, but it is a much more complicated machine. I didn't want to explain that over here, but this is a newer version of the same machine which gives you much better resolutions. And I can heat the lubricant and go to higher temperature. So this whole tribo contact will be in the lubricated condition. So here, and the interesting thing about this is I can change the normal load and I can independently control the energy of the system. So I can change the weight, I can change the length of the pendulum, which will change the frequency of oscillation. By changing the weight, I can change the energy that is input into the system independent of the tribo contact. And what this can also do is that we used a reed head, a rotary scale over here, which has got a resolution of 0.000219 degrees, non-contact one. So you see that the whole energy dissipated in the system is basically by the tribo contact plus the damping of the system. So if I don't have a tribo contact and I can get the damping of the system by this good, very high resolution scale over here, and if I have the tribo contact, I will get the energy dissipated by the tribo contact and the system. Both will be there in this. And seeing the difference, I can clearly get what is there in the tribo contact. So this is the kind of energy that the damping curve that is there when there is no load or no tribo contact. You see that it takes around 6,000 seconds to damp, which means that the system is having very low damping in no load conditions. And so we were studying, first we started off by studying stearic acid which is the standard, boundary lubricant that is studied in many ways. many places. So we did a test lubricant with 0.05 molar concentration of stearic acid in a base oil. Base oil is a standard base oil that we get from the market. And the normal load was kept at 10 Newton. The initial pendulum release angle was kept at 15 degrees. And we did 10 running in experiments from 13 to 16 degrees so that we get kind of steady state. We get steady state because then when we see the number of cycles it takes from 30 to 16, when it becomes constant, you know that it has reached the steady state. So it's a sphere on flat contact. And this is EN31 steel alloy for the disc and the ball bearing ball for the pin or the sphere. And temperatures we did from 27 degree to 60 degree and 100 degrees. And the maximum sliding velocity we got is 14 mm per second. And this really means the whole thing is taking place in the boundary lubrication thing. And as I mentioned before, the optical electrode had a very good resolution of 0.000219 degrees. So there is no stiffness altering system in the or sensor in the system. So when you see this at base oil, when I do the experiments at 27 degrees, 60 degrees and 100 degrees, as the viscosity reduces, I get higher and higher frictional force at lower velocities and even higher frictional forces at higher velocities. So this clearly can differentiate between different base oils. And when I add stearic acid, you can see the friction significantly reduces. And the interesting thing is that 27 degrees, the friction is higher, and at 60 degrees lower and 100 degrees it's still lower. Remember, this is the mixture of base oil and stearic acid. This is only the base oil. Base oil, actually the friction goes up. Here the friction drops, which means that stearic acid is playing a very important role in the boundary lubrication regime. So this is the color plot that we made, rectangular color plot. Here, the interesting thing in this machine is that the fretting part is not there because we don't have any stiffness, any loose things in the whole system. So we completely avoided the fretting wear regime. So only the sliding wear needs to be done here. You can see that at 27 degrees with base oil, the friction is relatively high. And when I put a base oil plus stearic acid, you can see the friction drops significantly, but at 100 degrees, the effect is much more. So with a simple visual map, I can say that this particular temperature and with stearic acid, I can get a much better lubrication characteristics. So we did some FTIR and XPS analysis to see the reasons for this. Clearly is because stearic acid is getting absorbed on the surface. So the effect of temperature on friction properties of the base oil and blend of base oil and stearic acid could be studied. Very good, very what you call low velocity studies could be done. And we got this published in a special issue for Nick Spencer in the Langmuir paper. So stearic acid effectively bonds on the N31 surface. So then that is when we approached Indian Oil and told that we would like to build another machine, and they supported us. But interesting thing is they wanted also noise and vibration data that comes from the machine. So which we didn't have in the earlier machine. So we built another machine of similar configuration as the previous one. The only difference being that the pendulum was heavier and we had bearings over here. And same thing where we have a lubricant which can be heated. And apart from this, we have an accelerometer that is attached, and we also have a what do you call a noise microphone stand to pick up the noise that comes out of this system. So same properties it had, but this machine we made it still stiffer, even stiffer than what we made for the previous version. So this shows you the system, basically the pictures of this. This is the disc and this is the tribo contact which is immersed in the oil. We have a big pendulum that is oscillating over here. The loads are quite large. And this whole thing was kept in a hemi-anechoic chamber so that we can pick up the noise and the vibration that comes out of this. And remember, there is no other noise producing thing. You don't have a motor that produces noise. So under no load conditions, whatever we pick up with the accelerometer and microphone gives you under no load condition, whatever the bearing noises and other things that are produced. Under the tribo contact, and if you take the difference, I can get the microphone and accelerometer noises, where I can get from the tribo contact what exactly is happening. So this is the microphone and the accelerometer we used. We used BNC things. And now I would like to introduce to you how we analyze the noise and vibration analysis. So one of the simplest analysis is to do an FFT to see what frequencies are existing. But we also went into what is called wavelet analysis. Many of you will be knowing what a wavelet analysis. Kindly pardon me if I'm patronizing you people. But the interesting thing about the wavelet analysis, which is different from the FFT, is that from FFT, if I get a FFT signal, I can't rebuild this wave back. For example, if I take this is a wave which is non-continuous, and this is a wave which has got all these frequencies. If I do the FFT of this and this, it will be the same. But given this FFT, I cannot say is this the signal or this the signal. So wavelet analysis helps you give the time domain data also, so that if I take this kind of a wave, you can see that at low frequencies, lower time, the frequencies are lower. I can pick that up here. And as I'm changing the frequency, it picks up at what frequency that is happening, exactly that's happening, frequencies that are happening here. And if I have a continuous wave, I can get all the frequencies that are there. So it clearly picks up 1, 2, 3, 4, and all of them together over here. So that's basically the wavelet analysis. So what we did was we did experiments again to confirm whether this machine is working, the similar kind of a thing, tribo contact sample preparation, no load, and running an experiment, sliding experiment, result analysis, and tribo film characterization. So the initial work we did was with these conditions, which initial pendulum release angle was changed to 25 degrees so that the energy input is larger. And here we could get much higher sliding velocities of 15 millimeter per second. And same optical encoder with same this thing was used with high frequency data collection. We could, this particular system that we had here, we can go to 10 megahertz data collection rate. So this is the no load experiment, which goes up to 5,000 seconds, 4,500 seconds. And this is the sound pressure variation level at that. Remember, you don't get any vibrational data because there is no tribo contact. And when we add ZDDP, which is a standard, what do you call, extreme pressure additive, you can see that, and or anti-wear additive, you can see that this has significantly improved, changed the damping time. So this is only base oil, it has come down to 1,000 seconds. But if I use ZDDP in that, I can go up to 2,000 seconds, 2,000 seconds plus, which means that it is a very good additive even for lowering friction. And this is how we got the coefficient of friction. We can see that the coefficient of friction significantly drops with ZDDP. This being the amount of energy that is dissipated by the system. So same rectangular plot, which visually shows you that adding ZDDP can change the friction significantly, especially at the higher velocity region. And the lower velocity region also it reduces significantly when compared to without the ZDDP. The noise levels also during things significantly dropped from 40 dB to 36 dB. And wavelet analysis also clearly says that this frequency that is dropping or that is being arrested is basically in the low frequency regime. So clearly tells you that ZDDP is a better lubricant. And we also see here what happened is when I'm doing this analysis for this scale, I will not get able to discern this region. So what we did was we separated out that region separately. So this is the low frequency region separately, and this is the high frequency region. You can see that high frequency, the very high frequency just completely die down by using ZDP. And this is the vibration measurement, significant change in the vibrations of the system with base oil and ZDP. So from 0.62 VRMS, it has gone down to 0.043, which is less than, less than or more than an order of magnitude difference between those two things. So same with the vibration analysis, where we can see that there is a huge change in the amount of thing. And we can also see at what point these things happen. Some detailed analysis has still to be done at where exactly these noises are coming in the system or when the sliding. We did some analysis of the tribofilm formed, clearly showing zinc sulfur tribos film that is forming on this. So this we went to still higher magnitudes, higher amplifications of 220 nanometer. You can see that this film has got large amount of zinc and sulfur in that, which means that this and this it basically not a mechanically mixed layer that's happening. It's a surface film that is being developed. ZDDP, you should remember, though it has been studied for many years, there is a lot of debate on how exactly ZDDP really plays a good role. Wonderful work has been done by Hugh Spikes from Imperial College. So observations were that we were able to get what you call we are able to clearly differentiate or get data for just the base oil and ZDDP. We were able to see the differences very clearly over here. So having done this, we got several oils from Indian Oil. So they had two base oils, and one was 2.9 CST, other was 7.9 CST. And then there were samples. So this is basically the base oil 3 plus anti-wear additive, and sample 4 is base oil 2, second base oil additive with anti-wear. And as trade secrets, they didn't tell us what they were exactly adding, but we could what do you call we can guess what is happening over here. And then what are the kind of things? So this one is the base oil plus extreme pressure additive, and then finally it is with friction modifiers. So we studied these 8 different samples and the same kind of conditions that we used for the previous set of experiments. So here we also did experiments at room temperature 60 degree and 100 degrees. Room temperature data I'm not presenting because many of these things, reactions take place only 60 and above temperature. But between these 8 samples, sample 1, 2, 3, 4, 5, 6, 7, 8, I can see. So, for example, base oil 1 is not as good, or the lower CST 1 is not as good as in the boundary lubrication regime, whereas the base oil 2 with higher viscosity is better as a boundary lubricant when it is added plain. But when I take this and I use these anti-wear and all the other additives, I can see that the base oil 2 is much better than the base oil 1 plus the additives. So these tests, if you tell me, will take, with some experience in running the machine, this whole thing at 60 degrees and 100 degrees. So at 100 degrees also, we are able to clearly discern these differences in these oils. This can be done in less than a week. Okay, and then we can see the vibration data, significant difference between the base oils and the fully formulated oils. This is 7 and 8 are fully formulated oils. You can see there is significant change in the vibration data. So same with we did with wavelet analysis to show you where these noises are coming at points where the velocities are approaching the maximum velocities. Some more detailed analysis has to be done on this. So this is at 60 degrees. So up to sample 4, and this is from sample 4 to 8, where you can see the differences very clearly. And sample 8 actually shows you more noise data, sample 7 and 8, than vibration data than, let's say, with just one of the additives. So these are the values that we got, the VRMS values, significant differences between the base oils and things. So very fast and quick, and what do you say? And with good resolution, we can get these things. So vibration data you can see is significantly different. And when we do the wavelet analysis also, this is from sample 1 to 4 in the high frequency range, you can see that it significantly drops, and the fully formulated oils have a lower vibration data than 7 and 8 are fully formulated oils, which show that. So here also you can see the VRMS value is at 100 degrees is much lower for the noise value. And this is noise data at 60 degrees, again showing you several wavelet analysis curves to show how the high frequency noise. Sample 1 is a base oil, sample 2 is another base oil. You can see between sample 1 and 2, the kind of noise that is produced at low frequencies are completely different. And when you go to fully formulated oils, this is the low frequency regime. You can see that the noise levels are significantly lower, even when compared to sample 7, which is with the base oil 1 and the fully formulated oil. So this is the high frequency range CWT analysis, where you can see that there is high frequency noises which died down when you add these additives. So this goes to sample 8. You can see that the high frequency noise is not there. Because remember, these high frequency noises, when exposed to a longer period of time, can create discomfort for the persons around. So LEQ was done for these noise analysis, and there is significant difference, not significant, but we are able to pick up good differences in this, because remember, these are decibel values. They are log scale again. So there are good differences in these values. So these are 100 degrees, not going into the details, but clearly showing that your body lubrication or the base oil, there's a lot of noise that is developed at 100 degrees centigrade in the low frequency regime. And the fully formulated 7 and 8 have much lower noise levels than the other ones. Same in the high frequency range, but high frequency range base oil 1 may not be as good as at 100 degrees as base oil 2. And we are able to pick up again the differences with the CWT analysis, where your high frequency noises kind of completely die out. So this is LEQ for various oils, base oil 1, base oil 2 plus the formulated, and these two are the fully formulated oils. So noise results also show a very good understanding, gives you a very good understanding from what is happening in these oils. So what we did was then we graded these oils. So we can see that sample 8 is the best oil. So we put it as 1, and this is the worst. So we put it as 8. So we have different gradations, and we presented this data to Indian Oil, all these data. And what they told was the results from the established test of IOCL, because they have some industrial standard tests, which for one formulation might take a lot of time. This is done much faster, and we are able to pick up good, reliable data using this particular machine. So we have now built another tribometer. Those of you who want to visit my lab can come and see this tribometer, where instead of using a bearing, we are using what do you call air bearing, aerostatic bearing. So there the damping comes down even further. So your no load cycle, if I from 6,000 seconds, I go to something like 30,000 seconds. And if I use higher normal energy input in the initial stage, at some point your damping, it just doesn't die down. Even after 10 hours, the pendulum is still swinging, which means that if I get data for the low angles, I'll only get the tribo contact noise and vibration data from that. The other noises are almost non-existent, but there is some noise because of the air coming out of that. So we also then told, why don't we try other things? So we made different kinds of soaps. So soap 1 to soap 5 are basically made with fatty acids of different kinds. Soap 6, 7, and 8 are a mixture of these fatty acids. And so then we measure the hardness of the soap. From moderately hard to hard soaps we made. Soap solubility from insoluble to what do you call very soluble in the things. And then when we this one had 15% glycerin and 15% water in the soaps. And you can see that this machine is able to differentiate between soap. So what we are doing in the soap thing is we are using a PDMS spin, which mimics the skin. And on the soap, we dip the soap in water when you're doing dry experiments, and when you're doing wet experiments, it goes. These are all dry experimental data. You can see that we are able to discern the differences that. And then when we in the wet sliding conditions, what we found is that the soluble soaps have lower friction, and the moderately soluble have medium friction, and the insoluble soaps have much higher friction. So we are able to again find out with this we are able to find out which soaps are there. So we are still in the process of getting data of different structures of the soap and seeing how this would influence the thing. So that is the latest. This data was presented only today by the student. This was done by Prasad from ICT, and I'm just presenting you a fresh data. So what else can we do with this tribometer? So I told you we want to get Stribeck curve from a single swing, acceleration and deceleration. There's always been not much of debate. Is your acceleration Stribeck curve same as your deceleration Stribeck curve? In other words, when the friction is high at the low velocity region and then it reduces, when I start reducing the velocity, will it retrace the path or will it take a different path? It's an interesting study that can be done in this, because when I take data from one angle of the pendulum coming to the zero angle and then going to the other swing direction, this is an acceleration cycle and this will be a deceleration cycle. Still struggling with trying to get this data out and study this thing, but we'll get it ultimately. We have done some chocolate tribology. I have not presented that data. This work was done with in collaboration with Mark Mason in Imperial College, and we could see the differences. Again, it's the PDMS flat was the PDMS spin with different chocolates in between. How the chocolate concentration, the fat concentration, other things change the tribology of the chocolates. Some interesting data had come from that. Can we do skin skim? We can do skin skim tribology. We can use wine tribology. We can now build the new tribometer that we built with the air bearings. Also, we can do rolling sliding experiments. So what we plan to do there is have a rolling sliding, different loading sliding ratios so that we can study the effect of these rolling sliding ratios on the film formation, and then do a what you call, after you disconnect the motor when it is doing the rolling sliding experiments, and then do a pendulum test to discern what is, or to get data from the energy dissipation. Chain cycle tribology is something that we could do, and we could do very careful studies on, like the first graph that I showed you up after the Stribeck curve, on how stiffness of the system would and the inertia of the system would influence the Stribeck curve, especially in the stick slip region. So if I can change the stiffness of the arm that is holding this ball there, and I can clearly see how the stiffness would change the noise levels, vibration levels, and things. Study of tribofilm formation is also pretty easy in this. Study of surface topography on the friction is also possible in this, and several. We were also thinking, can we use it to use viscosity measurements also at low velocities. So with this, thank you very much for your attention. I hope I have completed the talk on time.
Thanks to you, Professor. Totally right on time. Well, we have 10 minutes for Q&A, but it was super interesting. Thanks for that.
Shall I stop sharing?
I'm sure that there are questions on the slides, but up to you.
Okay, fine. Yeah, but this is a picture taken from the Indian Institute of Science. Ours is a very green and a fantastic campus. We very silent campus, which happens to be in the center of Bangalore. Nice. And those of you who have not visited the Indian Institute of Science are welcome to come. I can tell you proudly that this is the best research institute in the country.
Thanks to you. You got a lot of applauses from the audience. Manas, you were going to say something?
No, it was a fantastic talk. Thank you so much, Professor. I think we need to take the questions, Savi.
Time is flying.
Yeah. Perfect.
So the first one is, if you don't mind unmuting yourself, because I think it's quite a complex question. This is from Paulo. Okay, go for it.
Shall I stop sharing? So is it a question that is typed in the chat?
No, I think it is in the chat, as well as Paulo can unmute and ask the question as well. It's fine.
I'll stop sharing in the sense, not stop sharing. I should have gone out of the, sorry. 1 minute. I'll come back to sharing. Just hold on. Share. I'll come out of that what you call presentation mode.
Perfect.
So then I can see the window also. And where do I see the chats?
To the right, meeting chat. I see that Paulo may have some issue unmuting himself. No worries.
Maybe. Can you hear me now?
Yes, we do. Yeah.
Okay,
Please.
excellent. Hi, Professor. Thank you very much for the presentation. My question is actually regarding this part of the pendulum machine. How do you decouple the effects of the bearings on the pendulum itself? Do you compare with the load versus without the load, or it's negligible? How is this?
What we do is, I'll show you the pendulum tribometer. You will understand that. The schematic of that. I go to that slide. Here. So I have a tribo contact here. I go to the schematic of that is clearer. Yeah. So
Yeah.
I have a what schematic is the same. Here you see there's a tribo contact, right?
Yeah.
I can remove this tribo contact. Okay. And then I swing the pendulum. So this is the curve I would get in no load condition. This is the second generation one we built. We would get this, and this is the no load curve for the where is the no load for the third one? I think this is the no load one, no load experiment for the second generation machine, where you can see it goes up to 6,000 seconds. And then I get an energy dissipation rate for this. And then when I have a tribo contact, I'll get a much lower time for the oscillations to die down. So the difference between this energy dissipation and this energy dissipation is clearly because of the tribo contact.
Yeah, I understood. Yeah, this is the difference then. My question would be regarding if you use the machine a lot of times, if the bearings from the pendulum starts to degrade, and you should always then make this difference, right? You should always keep the reference first, and then you.
Correct. So what we do is, when we do one set of experiments, when we go to the second series of experiments, we do again a no load test, so that we know if the bearings are degrading. But but now in the present machine we have aerostatic bearings, so there is no question of any degradation.
Okay, understood. Thank you.
Yeah.
Cool. Thank you. The next question is from Hosseini. It's it's very short, so I can do it myself. He's wondering if you did investigate the effects of anti-wear on extreme pressure additives simultaneously.
Yes, but we are not done in detail. But see, first part of the work was to convince the user that this machine can pick up the differences pretty fast. Okay, so that part is over. So detailed analysis of how these anti-wear additives and other things act is something that we have to do work on.
Okay. The next one is not a question. It's Professor Almikar Ramajo from Coimbra University. Raise your hand. Feel free to unmute yourself if it's okay.
Yeah. Thank you. Thank you for your nice presentation. I know very well this technique. I used this technique for more than 50 years ago. And we have published several works, especially for contact lens and so on. In fact, we used the technique more or less in the same period after Michel Delon and Emmanuel Rigaud. But this technique was introduced first time around 100 years ago by Bernard Tog, a physician that had been used this kind of application. And I was surprised because I expected to have not a linear decreasing, of the displacement over the time, but an exponential. In fact, in a contact friction, we have two main sources of degradation of energy. One is the viscous damping, and the other is the Coulomb damping. And these techniques are very good because we can separate these two influences. But for that, we have to solve the second order differential equation, a second order non-linear differential equation. And in that equation, of course, we have two sources of energy. One is the damping, and usually systems works well because they are subcritical damping systems. And the other is the friction itself. And we can in fact control the total energy of the system in order to change the sensitivity of the system to measure smallest or highest friction. And here I think that the friction is much higher than I expected. Even in your work, using exactly the same fatty acid as you have shown in the first set of results, you have obtained the result from around 3 to 8 minus 2 of friction coefficient. And of course, these values of friction coefficient of 0.4 or 0.5 are not typical or of this kind of lubricated system, even in linear lubrication.
Correct.
I expect it to have minus 2 or minus something. And another thing, I suppose that the differentiation between the two regions that you have, that you call it a fretting region and a sliding system, this is not fretting. In my opinion, in that case, the system is controlled by the rigidity of the two vertical bars. Because the rigidity of these two vertical bars are negligible during the sliding motion. And after, when we reduce the sliding motion, the energy is specially controlled by the deformation of these two springs. This is my opinion. Because
I agree with that.
Sorry, just more one thing. And even in that case, in fretting, especially if we have not total sliding, we cannot talk about friction coefficient. This is wrong because we have no sliding. We don't reach the friction limit. So we can talk about tangential force or something, but this is not the force that is correlated with friction coefficient. But in any case, I was surprised with the lot of very different applications that you have decided to apply this technique. Thank you.
Welcome. Yeah, I appreciate your comments made, and we have thought of all these things, and then of course there will be issues, some of the issues that you have raised, but we still do believe that I don't doubt the values that we have got from the machine. So the stiffness issues we are more or less addressed by having a very stiff system, but again we have to do experiments with various stiffness to see how stiffness would influence the tribo contact.
If you want, you can send me some lubricants if you want, and I can test lubricants using our pendulums for you, and after we can compare the results.
Yeah, so again I tell you, these lubricants were sent by Indian Oil, and I'm not sure if I'll be allowed to send these lubricants to you. But what they told was the results that we gave them matches with what they did with standard tests like HFRR and the Timken and what is the other thing, that MTM machine and all that. So it matches with that. So that is what they were excited about. Yeah.
I love the idea of sending samples, and Professor Milkar, if you could present them in a next webinar or coming nowhere, we will love that.
Yeah.
Cool. Time to move on, eh? Otherwise we're gonna, people have things to do.
Yeah. Perfect. I think there's one last question from Kamran Ahmad. So I think it's a pretty long question. So let me unmute Kamran. Maybe you can ask. Yeah. Kamran, can you unmute yourself and ask the question, please? Okay. All right. Oh, let me ask. The Stribeck curve demonstrates the transition between different lubrication regimes. Suppose you are designing a mechanical system that operates under varying speed, load, and lubricant viscosities. If you notice excessive wear, even at high speeds, where hydrodynamic lubrication is expected, what are the possible factors could be causing this unexpected behavior? And how would you troubleshoot and optimize system for better performance?
In the hydrodynamic lubrication.
Yes. That's the question.
Hydrodynamic lubrication, generally, you don't expect much wear. See, what happens in hydrodynamic systems, one of the things is that when I stop the machine and start the machine, it goes from hydrodynamic to boundary. And only after a certain RPM will hydrodynamic come. So, for example, if you are using in a steam turbine and other things, these hydrodynamic bearings are known to last for years. But the thing is that a steam turbine is not stopped at all. So each time you start and stop, you have a problem. And that's when the wear hits. So I don't think hydrodynamic will have any wear as such, but it could definitely not be zero, because anywhere there will be some fatigue loading taking place on the surface and there'll be small wear taking place.
Yes, I think, yeah, that should be our last question, Professor. And I really thank you for accepting our invitation and giving your talk. And it was really very insightful, and we had a good discussion as well. And I also thank all the participants. And yeah, that should be the end of our session. Thank you, Professor.
Okay, then. Bye, everybody.
Thank you. Bye.